بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين. Good evening everybody. This is Haytham Sadeq and today I will present my graduation project. We were 3 students at Qatar University in the Department of Civil Engineering, and my name is Haytham Adnan Sadeq and my colleagues are Rakan, Marwan Amro and Mohammed, Saleem, Taha. I am Arabic, but I will present this presentation in English and it will be available also in Arabic for your information. This project was supervised by Dr. Khaldoon, Bani-hani for the structural part, and Dr. Hisham for the foundation and research project, and Dr. Ahmed Al-senouci for the project management and planning for the project itself. As a start, we have designed in this graduation project the PAIR project, which is located in Qatar. This was a very special project because it was built in the sea, and building something in the sea was very important to study the stability of the structure on some man-made islands. This building is a 22-story residential floors plus the 2-car parking floors, and it is open to the water surface and for a very huge wind load on the building. As a start, if you see that this is a man-made island, and it was exactly as it's shown in the before left picture. As you can see, they filled that water by the sand for around 4.5 meter, and there were some 4.5 special before the backfilling of the soil. It was a seabed deposit, so to reach the rock for this layer was around 9 meter in the sand to support your foundation, and this will be discussed in the foundation part. As you can see, we have 3 main parts in our graduation project: the structural, foundation and management. In the structural, we did the design for the ribbed slab system in some of the floors, flat slab, shear walls as vertical member, and that was very important element in our graduation project, the columns, stairs, ramp and bearing walls. In the foundation part, we did analyzed the different foundation system that may be used in this structure, and we show how is it fit to this building or not by doing that procedure for different systems. And then we did a detailed design for the piled cap system that is chosen to be done for this project. We have some small parts which we also apply the isolated and strip footing design. At the end of the foundation part, we have participated with Dr. Hisham in the research, and it was about the concerns about the design of pile draft on rock, and it will be explained in this graduation project presentation. In the management part, we did a work breakdown structure for the building, we did the quantity estimation, and we scheduled the project using the Primavera P6 and considering all the relations between the activities. Starting with the structural analysis and design part. The design process for the graduation project was mainly moving with this diagram. First, we have understand the architectural of the building, because we get the architectural and it was a real design architecture with a very complicated details, so we spend a lot of time understanding this architecture, and then we go to the next stage, which is the analyzing and designing the floor systems, which is the flat slab and the ribbed. After that, we were able to develop the 3D model for the tower, and we used the program of ETABS. After that, we checked the 3D model stability using the stresses and the effect on the foundation and the lateral drifts and deflection. After we assure that the structure in a mass is adequate to check the stability, we go for designing the vertical members for that stability using the design for the shear walls and columns, special elements as stairs or ramps. After we finished the superstructure design, we went to the substructure design, which is the foundation system, which will be the part 2 of this graduation project presentation. As you can see here, I will move by the steps of the graduation project to know where we are. In the architecture, we have understand the AutoCAD plans, and we were concentrated on the main part that connects the structure with the architecture, which is the columns, sizes, and locations. From the architecture drawings, we can get the design loads, which will be used in the analysis of the slabs. We start to analyze and design the floor system. The first one was the ribbed slab. It was designed with different ribs and different beams. The ribs was supported by the main beams, and some of the beams were designed for flexure and shear only, and some of them, which is the parameter beams, was designed also for torsion. The floor design cycle was starting by selecting a preliminary beam sizes, analyzing the floor using the safe, and then check the maximum deflection with the allowable, and then confirm the sizes of the beams and go for reinforcement. This is the safe analysis, and this is the ribbed slab system that was used in this floor. This is the general detailing of the ribbed slab. It was designed as a rib, as a T-beam. This is a sample of the beam that was an exterior beam, which is flexural to resist flexure, shear, and torsion. This is the next slab system, which is the flat slab residential system. You can see the strips that we have divided to design the flat slab. Actually, we have an irregular shape, so we use the safe to analyze the strips. And also bunching shear check, we get the critical points, and then we check it manually to know if the slab will be adequate to resist the shear, the bunching shear check. This is a general detailing of a section of the flat slab. Also, this is the different flat slab, which is the basement flat slab, which is also have been designed as strips and for positive and negative. For the 3D structural system, this is the important part. We have designed it for wind, and the main member to resist the wind was the shear walls. And this system was mainly used because we have a huge shear walls depending comparing to the columns. So we have neglected the rigidity of the columns, and we consider that the rigidity is connected with the diaphragm action to the shear walls only. And the columns has been assumed to be a pinned end. This assumption is discussable, but some of the professors are really agree to assume the concrete, which is not detailed in a special detailing, as pin. And if some structures need some special detailing for rigid beam to column connection, which I will present it in a different presentation, but assuming it's a pin column is more conservative. Why should we do a 3D modeling? This is the question that is always asked. Why should I make a 3D model? First of all, to check the stability of the structure and the deflection and the drift values, and to get the column loads and the shear walls when the wind is applied. Also, if you are applying the seismic, or you are applying a blast, or applying any other load, it will be different if you analyze it as a 3D or 2D. After that, we will get the reactions, and we will get it to the foundation system. The ETABS modeling. The ETABS modeling was a very important part in our presentation, in our project, because we have used the manual meshing to mesh the slabs and connect it with the columns and the shear walls. This was a very important step to assure that the finite element software is working properly. The ETABS modeling also, in the piers and spandrel system that is used, we can put the spandrel to transfer the load horizontally to the piers, and putting the piers as a vertical members to take the loads to the down floors. The load combination that we have taken is assumed by the ACI 2005. In the manual wind load calculation, we have taken the exposure D because the structure was open to the water surface, and we have taken the category of the building is 3 because the importance factor is 1.15 because it will be full of people, and the basic wind speed as have been discussed with the major consultants in Qatar, which is 150 km per hour, 41.7 meter per second, and because it's around 23, it was very empirical to calculate that it's a flexible building in the dynamic analysis, and the natural period estimated was 1.36 seconds. Computed gust factor was equal to 0.873. The ETABS is generating the wind load automatically, so we have used the command of the ETAB to check our calculations manually, and we have inserted the CP, the windward coefficient, and the leeward coefficients, and we have considered that we have only one case, which is the most probable case, the critical case, and we have taken from the ground to the roof, and including a parapet of 1000 millimeter with the wind speed that we choose it by mile per hour, and the exposure and the gust factor and the directionally factor KD, topography factor KSD is equal to 1. This is a comparison between the manual and the computer wind analysis calculations. You can see this axis is the wind force, which is per floor kilonewton, and the elevation. As you can see that the values are very near, and this is why we have been assured that our values and results is true. And using some lateral deflection analysis in the ETABS, we can check the deflection. This is a video, but it's not working because a technical problem. It cannot be shown in this video, but if you want it will be available on YouTube to see the deflection of the building with the lateral load. Also after that, we can check the lateral deflection check, the drift with the maximum deflection per the total height. The maximum deflection we get it around 56 millimeter over the 84 meter. We can get that the ratio is less than the 1/500 specified in the code. And we have checked the interstory drift, which is the maximum deformation at the top of the story minus the deformation of the bottom of the story divided by the height of the story. You can get this value, which is 0.00082, and it is less than the interstory limit, which is the height over the 500. This is the dynamic values, the dynamic output from ETAB. He gave me some period time, which is 1.98, which is actually more than the was calculated using the empirical calculation, and this is because the ETABS is considering all the geometry of the building in his analysis, in its analysis. So the period is usually bigger in the finite element softwares than the empirical values. Now we reach the design of the most important. As you can see in this part, we have understand the architecture, analyze the design and the floor systems, perform the 3D analysis, and go to the 3D model stability. After that, we can go to the vertical members, and starting by the major part of this building, which is the shear walls. We have divided to different piers, but it was designed as one core. And we have did this by considering all the load, all the principal forces. We consider the axial load that is coming for each pier, the moment on the strong axis, the moment in the weak axis, the shear in the strong axis, and the shear of the weak axis, and we have considered the torsion. To design all of these values in one time for each floor, for each pier, for each load combination, it will take million of time to present it. So this is why we have put in all the equations that we used in the design to check the axial load capacity and to determine the horizontal reinforcement, and using this horizontal reinforcement we can determine the vertical reinforcement using for the maximum moment in the strong axis and the torsion, and after that we can check the axial load with the weak axis point if it is covered or not. To do this, we have developed a macro function. It was a very unique function, Excel function, which were easy to import the data from the ETABS for all the principal forces and copying it to some equations that design the shear wall for each floor, for each load combination. So because it's not always critical to take the maximum axial and maximum torsion, maximum shear, maximum moment, because sometimes the axial load is helping the design of the shear. So we have to design it case by case, load combination by load combination, story by story. This is why we have developed this macro function, and it was very efficient to give a huge data in a very fast time. We have analyzed the shear walls using ETAB, export them as a text file, all the load combination, then copy all wall forces in an Excel file, which is prepared to take this Excel text file from the ETAB. This forces is copied in the macro function for each floor for one load combination, and then we run the macro and get the design results. We apply this for all load combinations and then take the largest amount of rebar depending on the load combination. Group the floors and according to the rebars and go for the detailing. This is the result for each pier, as you can see, for each floor. And this number, for example, 120, this is coming from the 6 or 8 load combination that we have used in this floor. As you can see, this floor, which is the 11, has a reinforcement more than the rib, which is the first one or second one. This is because it's dependent on the torsion, shear, and not only the axial and the moment. After that, we group these values and we take them for the detailing, as you can see in this drawing. This is the elevation of the detailing to show the opening with the slab. Now we reach the column design. We have designed the column as pinned column, and this assumption is a very conservative because you are taking all the loads to the shear walls. And we have a lot of discussion about this, and we will separate a presentation clarifying the problem of the rigid connection of the beam or the floor column connection and the simple connection, and why we can do a pin column connection in concrete structure or not. This will be displayed in a separate presentation. We have designed it as a pin end in this graduation project. We take the axial and we check the reinforcement. This is the column types, and this is a sample detailing of some of the columns. Ramp design was designed a very simple way, which is using a one-way slab system. We have distributed the load of the ramp to the beams that is supported on the columns, as was shown previously. This is the details of the beam, which is the continuous beam that holding this ramp. And we have also designed one of the pier walls. This pier walls was surrounding the building. It was designed for a moment on the weak axis per meter. And this is the general details of this bearing wall. The stairs was a very nice structure, which is we consider it as fixed with the shear walls in order to minimize the moment, and we get the negative values and the positive value using stats software, and then we designed this stair as a continuous beam supported on the shear walls. As you can see, this is the negative reinforcement that is detailed in a very correct way, because we have to make sure that all these junction is available and able to resist this tension. Now we reach the foundation analysis and design part. Mainly we have 4 divisions in this part. The first one, we will explore how did we check the foundation system for the tower. We have checked the raft only, and we showed if it is available or if it will be okay to design as a raft or not, and then we will go for the piled raft, and then we will use the pile cap system, and it will be illustrated. The car parking foundation system, which is just 2-story building, we have used the isolated footing and strip footing. And in the research part, we check the pile load share research, which is describing the concerns about the design of the piled raft on rock or on the piles that is socketed into rock. And it will be exploring the concerns and the errors that can be done in estimation the subgrade reaction and the pile spring constant. As a final part, it will be the design of the sheet pile wall, which is using the cantilever system. Here, as you can see, that this is the tower area, and in this tower area you can see that we will use the high capacity foundation system, and this is the car parking area, which we use the spread footing and the single footing for the foundation. for calculating the raft foundation, if we want to do raft, we have to check the settlement, and we assume that this is the sand because it's a man-made island and we have some sand, 9 meter. Then the rock will start with an average RQD of 45%. When we check the settlement, the sand of the settlement was 7.1 centimeter and the rock settlement was 8.5 centimeter. The maximum allowable settlement in the raft is 10 centimeter, and it will not be allowed to use the raft foundation in the system. And we showed all the details and the calculation to show that it will not be adequate for this system. So we switch to the pile draft system. The pile draft system, the first procedure, the first step in the procedure of the pile draft, that we have to calculate the pile capacity. And to calculate the pile capacity, we have to know what is the rock that is surrounding and the friction with the rock, and how we are going to transfer the load of the raft using the piles to a stiffened strata of the rock. To estimate the number of the piles, if we want to use just a conventional pile draft, we will know what is the total surface reaction, and we will divide it by the pile design capacity. We can check how many piles, and we distribute it equally. But we had a problem that some of the columns are concentrating on more piles than others. For example, if we take this column is putting more load in this pile, so this pile is not adequate, and it is not distributing the load of this column for all piles, even if you used a rigid raft. So we have tried to go to the pile cap system. The pile cap system is using, you can group the columns. We use the middle raft to take the shear walls and the major columns by a raft and distributing it to the piles, and for the other columns we can put the pile cap system for each control for each columns. Also, we have some problems in this. We have to increase the thickness of the pile cap, or we have to increase the number of the piles. The final layout that we have reached with the number of piles and number for each column, as you can see in this, and it will be there will be a raft with a 50 centimeter surrounding these pile caps. This is the safe model, and we have checked that the reaction coming to the pile is less than the pile capacity, and this will be an adequate design. This is sample detailing of the middle raft for the shear walls. This is a section, and this is a sample detailing of the pile cap that is carrying one column, and this is the section. Now we reach the car parking foundation system. We have used the rectangular footings, and this footings was surrounding in the car parking area. Sample detailing of the rectangular footing is this. We have used also a wall footing for the bearing wall with a very simple method for the designing of the strip footing. This is a video was prepared also in the graduation project to model the foundation system in this structure, and it will be shown in a separate video. This is the cantilever sheet pile. We have proposed that we can put a sheet pile to resist the soil, and we can use this system as a marina. This sheet pile can be very easy analyzed using the earth pressure calculation. As you can see here in the figure, we can calculate the earth pressure from the soil, the water, and we designed this pile sheet as a cantilever pile sheet. We have chosen to do this pile sheet as a contiguous piles because we are not required to make it impermeable. We can let the water go because it's already the water is surrounding the pile sheet. Now we have reached the research in the geotechnical concerns about the design of the pile draft on rocks. We know that we have two concepts in the design of the raft on piles. The first one is the conventional concept, which assuming that the stresses that is coming from the raft is distributed to the piles directly, and there is nothing sharing the loads from the surrounding soil or rock. The other type is the pile draft concept. The pile draft is considering the spring constant of the pile and the subgrade reaction of the rock. In these two modeling for this raft foundation, we are assuming the modulus of subgrade reaction, and we are assuming the pile spring constant. And the assumption of these values these values have some ranges, and if we assume it in some way, we can affect our design. And this is what the research is exploring. What we have did, we know that the spring subgrade modulus of the rock, for example, ranges from 150 to 300 in Qatar, and the pile spring constant ranges from 4.5 to 9 meters, depending on the RQD of the rock surrounding the pile. And we have some raft foundation with a spacing of 3D up to 60, and we can use thickness of 0.75 or 1.2 model, or simulate the thickness of the raft if it's a rigid 1.5 or a flexible raft. We have considered two types of the piles: the piles which is embedded in the rock, fully embedded, and this is the case of Qatar in Corniche. Depending on the RQD, different RQD, we can get different pile spring constant. And there is another type which is the pile that is socketed into the rock, which is the system that, or the strata of the other countries, not here in Qatar. Some areas like the Pearl Qatar or the New Doha International Airport, they have the same type of these piles, but in the Corniche area you will see that the piles is fully embedded in the rock. We have taken this spring constant, and we have checked all these values that we have described here for all cases to describe the errors that can be done using the assumption of overestimating or underestimating either the spring constant or the subgrade reaction. To calculate the spring pile constant, we can go to the pile load test, and using the load we can take the slope. This is the range, and it can be 9 meganewton per millimeter. If we go for another RQD, we can reach 4.5 for the same pile which is embedded in the rock. So this ranges can depend and can differ the results of the design. As you can see in these figures, what we have did, we choose to make a pile draft with a 25 piles with a spacing of 3D, and we assume that in the finite element, using safe software, in the finite element we have assumed that the pile constant, the pile spring constant, is 9 meganewton, one, and in another case we have assumed that it's 4.5 meganewton, and then we check how much the pile load is sharing in each case. As you can see that the pile load sharing is less when we have less spring constant, because the pile is weaker and the soil is the rock is taking more. In this case, the difference between these assumptions can take the pile load. If we assume that the pile is 4.5 and then we reach 9 meganewton, so the pile will take more load and maybe it will not be adequate to resist this wall. We have also did this for 6D, spacing of 60, and this was very huge difference, because here you see that the pile load share is much smaller, and the difference also can be because of the wrong assumption of the pile spring constant, or if we assume that the subgrade reaction is 150 and then we reach 300, so the pile load share will be less and the subgrade will be more. We have to estimate both of them, because if we assume also any numbers, it can give other results for the pile load share and the subgrade reaction share. For the other case, which is the pile is socketed into the rock, we calculate the pile constant, which is 1.5 meganewton per millimeter, and this is the difference using the 1.5 also for 3D and 60. And as you can see that in the 60 you have difference even for the rigid raft or the flexible raft. Conclusion of the research, that you have to make an accurate determination of the pile spring constant and the subgrade reaction. We can do the pile load test before the design stage, before we finalize the design, because it will affect the design of the foundation. So avoiding double error is much better than doing double error, or making one error is better than doing double error. The last part of our graduation project is the project management and the scheduling for the project. We have 4 divisions, which is the work breakdown structure, the quantity estimation, the cost comparison between the ribbed slab and the flat slab, and the project scheduling using P6. Primavera P6. The first one is, this is the work breakdown structure. As you can see, project, we have divided for site preparation work, substructure, superstructure, and the marina. For the site preparation, we need mobilization surveying, and substructure, we need piles, foundation work. In the substructure, we will go for car parking floors and the ground floors up to the 22. In the quantity estimation, we need the materials. The concrete, we have around 7,500 meter cubic, the concrete 40, the concrete 50, and the steel, we have calculated how much total, and the vertical formwork, the horizontal formwork. The labors, we need some labors, mason, vibration, steel fixer, carpenters. We have only calculated the labors and the material related to the structural members. We did not include the architectural members or any mechanical equipments that will be on the site. The resource planning, we have given the resource cost rate for each labor or the equipment, for the excavator, trucks, tower, crane, steel, the major things in the brand, and we took the productivity of each activity. We have comparing between the ribbed slab and the flat slab, and we were fixing the duration and playing with the labor that can be used or the cost, and we can compare the activities of ribbed slab and the flat if we either fixed the duration or fixed the labor numbers and the productivity. So we fixed the duration and we compare the cost between the flat slab and the ribbed slab. The ribbed slab was 33% cost increase, and this is why, because the ribbed slab is full of ribs and formworks, and this will be very costly. In the project scheduling, we have used the Primavera, and we have put in all the relations between the floors, and we checked the S-curve of the structure, which is describing the cost per the time for the project. This is the labor histogram, and this is what, because we initially we will need some huge number of labors, then we will decrease the number of the labors in this site. For the structural members only, we have calculated the cost, and it will reach 40 million Qatar Riyal. The total duration for structural members only around 2 years. This is depending on one shift, depending on a certain number of labors, not a huge number. The starting date will be whatever, and completion date is whatever. Project conclusion, we have applied the theoretical knowledge into a real project and real architecture constraints, and we have worked and followed the design codes that is available into the field. We have improved our engineering skills, our self-learning, our time management. We know how to work in a team, we know how to manage our conflict, and we know how to solve the problem that we face in the project. We are very happy in this project, and we did a great job. And we really thank everybody that helped us in this graduation project, especially our professors and our colleagues, our fathers, our mothers, everyone who participate in this project. Thank you very much, and you are welcome to ask any question if you have one. Thank you.